I'm Janelle Marie and I'm with Petunia Pentagon to help make math just a little bit more fun. So today we'll be practicing operation with vectors in 3D dimensional space. We'll be going through some problems and questions together today. And so if you're ready with your calculator, pencil, and paper, let's get right into it.
You can see my screen. Let's get started. So, what are our learning goals today? So, our goals are to practice addition, subtraction, and multiplication of vectors in 3D dimensional space. We are to apply mathematical operations to vectors to find magnitude as well as unknown values such as coordinates, and we will be determining vertices of a parallelepiped. So the first section we'll be going through is addition and subtraction. The first problem is given vectors u and v, solve for u plus v, and then part b is solve for u subtract v. So we're going to use this visual over here. If you see, we see vector u here, and then v here. We connect it tail, head, and we result in this gray vector on here. To figure this out, we're going to write down u plus v. We're going to be adding their components essentially. So let's just rewrite the vectors. So -4, 6, -3, plus 7, -5, and 2. We're going to break it down into, so the x is -4 plus 7. Then we have the y, 6 subtract 5, because adding a negative number is equivalent to just subtracting that number. And then we have -3 subtract 2 for the z component. And there's just simple addition. So sorry. I don't know why I was subtracting there. -4 plus 7 is 3. 6 subtract 5 is 1. And then -3 plus 2 is -1. That is our answer for the very first question. Now we're going to go into subtraction. We're going to look at the visual again. We have vector u. And the reason why vector v is going in the opposite direction is because we are subtracting it. We know that vector quantities have direction and magnitude. That's why they're different from scalar quantities. And the negative indicates the opposite direction, which is why v is going downward instead of upward now. And then that results into the gray vector once again. Now to solve that gray vector, let's rewrite u subtract v this time. And so just rewriting the given vectors. Now we're going to subtract -5 and 2. We have -4 subtract 7. We have 6. Now that we're subtracting a negative, we can just add 5 because it's equivalent. -3 subtract 2. We're going to end up with -11, 11, and -5. So that is our answer for the second practice problem. Now we're going to go on to our second section of this practice lesson, which is multiplication and magnitude, but more specifically we'll be practicing how to multiply a scalar with a vector. So it says find the magnitude of the combination of vectors a and b if a equals -1, 3, and 4, and b equals -4, 1, and 2. So we're going to be applying subtraction, multiplication, and magnitude all in one question. But before we go into magnitude, let's just focus on the other two operations. So recall BEDMAS rules, okay? We're going to be multiplying before we subtract. So I'm just going to write 2, and then vector a is -1, 3, and 4. Subtract -4, 1, and 2. We're going to do the same. We're just going to multiply the 2 into the first vector. 2 times -1 is -2. 2 times 3 is 6. 2 times 4 is 8. And then we're just going to rewrite the second vector here. Now we're just going to do subtraction. -2 minus -4 is equivalent to just adding 4. 6 subtract 1 and 8 subtract 2. And if we do this, that's just 2, then 6 subtract 1 is 5, and 8 subtract 2 is 6. So that is the vector. Now we aren't done yet because we have to find the magnitude. If we recall, we just learned the formula of it, which is that. And we're just going to plug in our values once again. So 2 squared plus 5 squared plus 6 squared, all under square root. We have 4 plus 25 plus 36 should equal 65. And because we don't like decimal numbers, we're going to keep that as our final answer. That's our lowest terms. Now, the last section that we'll be going over is we're going to be applying all our operations to find unknown values and vertices of 2D and 3D shapes. Suppose that A, B, C, D is a parallelogram, as we see right here. Given the values below, solve for the coordinates A and B. If we look at vertex D and vertex B, they're missing a coordinate. That's what we're looking for. There are two ways to approach this question. We see that vector AB and DC are equal. Why are they equal? Well, we know that vectors are equal when they're equal in magnitude and are going in the same direction. Now, this also holds true for A to D is equivalent to vector BC. Just for time purposes, we're just going to do one method today, and we're going to choose the one that's in teal. So we're going to solve for AB, and we're also going to solve for DC. Now, if you recall how to find a vector given 2 points, you're just going to do head, subtract its tail, and in this case, it's going to be B subtract A. So we're going to write B, which is -2, B, subtract A, which is -5, and 4. We're going to write the same thing for D and C. So we're starting out with C, which is 2 and 4, minus A and 1. We're going to solve for AB first. -2, subtract -5 is just the same as adding 5. And then B subtract 4, simplify the first x component, which would just be 3. B subtract 4. Now we're going to do DC, 2 subtract A, 4 subtract 1, simplify the y component, 2 subtract A, and 3. Now, how do we solve for the A and B? You may be wondering. Well, we already said that AB is equivalent to DC, so all we have to do is make them equivalent. So 3, B subtract 4, and then 2 subtract A, 3. We can break this into 2, so 3 will equal 2 subtract A, and over here it can be B subtract 4 will equal 3. Now, simple, just algebra, finding the value of A. Moving this here and moving this here, we go A equals -1 because 2 subtract 3 is -1. We can just move over the 4 by adding it. And so B would then equal 7. So those are our final answers. A equals -1. Let's use yellow to stay consistent. And B equals 7. Okay, now we're going to go on to our last problem. So a parallelepiped is determined by these following concurrent vectors. Remember that concurrent means they meet at one point. In this case, it is the origin. Now, we're going to use the image because it would be helpful as a guide, even though, it's not graphed properly, like the points. We're just going to use it so we can conceptualize what's happening here. And I'm just going to label vector OA right here, OB here, and OC, and you're going to see why. Now, we have to find 8 vertices, but technically we are given already 4 of them, so we just need to find the other 4. Technically, A over here would be -2, 2, and 5, and same for B and C. So to find the other vertices, you may be like, what should we do? So we're going to be adding vectors, because if you actually see, we're combining vectors to reach a point. So OA, example, plus OB, remember you can just rearrange vectors however you'd want to reach this point. We're going to write that down, write that combination down, OA plus OB. And then another combination that we can do is OA plus OC to reach this point. I'm going to write that down. We can also do OB and OC. I'll show you that, OB, OC for this bottom vertex right there. Write that down. Now, how do we get to that top vertex on the right? Well, we can add all 3 vectors that we are given together. So we can go OA plus OB plus OC. I did that the opposite way. Actually, it does not matter the order when you're adding, but just to keep things organized, we're going to go by the order of the alphabet. Almost forgot the little hat over there. Plus OC. And we're going to rewrite all the vectors and then add them together. I think I actually wrote down B here instead of C. And we're going to copy this. Okay, beautiful. And now we just add them. So -2 plus 0 is -2. 2 plus 4 is 6. And then 5 plus 1 is 6. So that is our first answer for this vertex over here. I'm going to write that actually. 6 and 6. -2 plus 0 is again -2. 2 plus 5 is 7. And 5 plus -1 is 5 minus 1. So that's going to be 2, -2, 7, and 4, which will be this point here. -2, 7, and 4. I find that it's really helpful to label your parallelepiped, even if you like draw one that's not to scale or not graphed. It just helps you organize your thoughts. Next one is 0 plus 0 is of course going to be 0. 4 plus 5 is 9. And 1 plus -1 is 1 minus 1, so that's just going to be 0. And that one's going to be this bottom vertex right here. 0, 9, 0. Now we're going to add all three. I'm going to write this down so you can understand what I'm doing. So -2 plus 0 plus 0. Then we have 2 plus 4 plus 5. Then we have 5 plus 1 subtract 1. -2 plus 0 plus 0. -2. 2 plus 4 is 6 plus 5 is 11. And 5 plus 1 subtract 1 is just going to be 5. And we can just add that on the top here. And now we can just highlight all of our answers. Alright, beautiful. Again, the other 4 is of course the origin, and then these technically are point values. So just to sum it all up for you guys, I just have this little chart with what we learned. So we have addition and subtraction, which we add each of the components to equal a vector quantity, or if you looked at the parallelepiped example, we found a point. It depends. Multiplication, multiplying a scalar with a vector. We multiplied the number into each of the components to get a vector quantity. Now with magnitude, we have to square the x, y, and z components and then square root it to get a scalar quantity, which usually it's d number of units.
So that is all that we have planned for today. Hopefully you enjoyed this video, learned something, gained some help on like a particular type of question, or just were able to practice your skills regarding operations with vectors. Otherwise, on behalf of Petunia, Pentagon, and I thank you so much for watching this video, and I hope you have a lovely rest of your day. Stay smart, guys!